Great. Now that we've selected our variables, now we want to know the model that we have here. Is it accurate or not, right? So question number 3 talks about model fit. It talks about model fit, right? So the question could be something like, let's see, do I have the questions here? Let me see if I have the questions so I can say the question nicely. So the question could be, how well does the model fit the data? How well does the model fit the data? Very good question, right? So if you remember well, we said we're going to use R squared, right? We're going to use R squared. And in the advertising data, the model that uses all media, the model that uses TV, radio, and newspaper, it has an R squared equal to 0.8972. I don't think I've talked about R squared when it comes to multiple linear regression, but it is the same case. It is the same case. Excuse me. It is the same case as in the linear model. In the linear model, we said our R squared will be equal to the correlation between X and Y squared, right? In multiple linear regression, your R squared is not this exactly. I think I remember mentioning that there is a slight difference. It is because our R squared is equal to the correlation between Y and your predicted values. The square of the correlation between response and fitted linear model and the fitted values like that, right? So the property, like in the simple linear model, it was trying to minimize this. If you remember well, it was trying to minimize. It was trying to maximize this. It was trying to maximize the correlation, which is like maximizing R squared. That's the same case here. It's trying to maximize the correlation, and it would make sense. If there's high correlation between the actual and what we have predicted, then it means we have fitted this thing nicely, right? It means we have fitted it nicely because there's high correlation between actual and my predicted values. Cool, right? So it's trying to maximize this. It's trying to maximize this, maximize that, which is like maximizing to get the largest R squared. That is the best model. That is the largest R squared. So in our in our advertising, our sales, right? The TV, radio, newspaper model, that is all three, it is an R squared of 0.8972. And the model that uses only TV and radio, it will have an R squared equal to 0.89719. Interesting. Do you see what just happened here? When we added newspaper to the TV radio model, see, the TV radio model had an R squared of 0.89719, and when we added the newspaper, it jumped to 0.8972. So there's a slight increase, right? And if you remember well, our p-value for newspaper was saying this thing is useless. Newspaper is completely useless. But here we see that even though it's very, very tiny, but we see that there is an increase in R squared. There is an increase in R squared here. Even though it's very, very tiny, sometimes you can't really see it, but there is an increase. And what's funny is it's happening because we added something that is useless to the model, which is a very important fact. Because it turns out that R squared will always increase when more variables are added to the model, even if those variables are only weakly associated with the response. So even if you add noise, whatever it is, things that are not even things that are weakly associated with the response and stuff, like this newspaper, very, very weakly associated, but it will always increase the R squared, right? And the fact for that is very simple. It is because when we add another variable to the least squares equation, that equation, right, it will allow us to fit the training data more accurately. That's R squared, the one that measures how we are fitting our training data, R squared will increase. R squared will increase because now we are fitting more training data accurately, just for the mere fact that we have added this noise here, right? So as you add more variables, you are fitting the training data more accurately, reaching a point. You remember that point of what? Of overfitting and stuff like that. But on the training data, you will say, you're doing perfectly. We say you're doing perfectly. But now the case will be when we go to test data, this newspaper might actually even cause problems, because it is not very useful in the model to capture the trends in the model. Although R squared increased, but it is not enough for us to just use R squared to say, this is a better model. No, it's not enough, because R squared measures on training data, and our what do you call this? Our concern is with test data that the model has never seen before. So if we just chose R squared because it increased, we're going to be wrong, because this newspaper, when you put test data into a model that is TV, radio, and newspaper, this newspaper part here, it will most probably lead to fake results or wrong results, because this is a low p-value, and we have been told that this is not very useful in the overall model. It is not very useful. So when you put our test data, it's going to give us wrong results, right? So be very careful. I've seen many people who are starting out in machine learning. They just go for the model that is the highest R squared, but not really. R squared always increases. It always increases as you add more variables. Be careful. Maybe you might be adding noise. You are just making training data happy, but test data, when it comes, your model will break. Right? So cool. One other thing that you can look at. The one with with TV only, the R squared with TV only, it was 0.61. It was 0.61. That was the R squared. So can you see, TV only was 0.61. When we added radio, it jumped to 0.89. That is a huge jump. I will be happy with that jump. And you can compare now the other measure, because this was the first measure. This was the second measure that we discussed. What about the first measure that we discussed, called RSE? If you remember, the RSE for TV and radio model is equal to 1.681. And the one with newspaper, so TV, radio, newspaper, the residual standard error, the RSE, is equal to 1.686. Let's see the one for TV only. One for TV only is 3.26. So if you start with the one for TV only, like 3.26, and when you add radio, it goes down by a very significant amount, from 3.26 down to 1.68. This is a huge drop in the error, in the residual standard error. So you'll be happy. You'll be like, yes, radio, I think is significant. Let's look at the R squared. The R squared jumped when I added radio. It jumped from 0.61 to 0.89. So radio. So for both you are satisfied that radio is a good one, right? Now look at the RSE when we add newspaper. It actually goes up from 0.681 to 0.686. It actually goes up, which means we have introduced some noise by introducing this R squared. Although by introducing newspaper, although for our R squared it increased, if we just look at R squared, you get wrong results, because our RSE, look at our RSE, our errors have actually increased by including newspaper. So you can see that now this corroborates, it is in the same line with the previous conclusion that a model that uses TV and radio is much more accurate than one that uses TV spending only, and better than the one that uses all three, that includes newspaper. So this video was for model fit. Model fit, try look at all these RSE, R squared. Try to see how these are changing as you are adding your variables, and take cognizant of the p-values, because the R squared can lead to increasing R squared, increasing R squared can lead to very wrong results when you start applying your test data. So in the next video, we're just going to do the last question, which is predictions. And the question is going to just look at how well are we going to predict unknown data.